So, in the last class we talked about symbolic model checking, right. So, by using fixed point computations we were able to find out whether different properties hold on different states of the system. Now, as we know that the main problem that is there in model checking is the capacity issue, and that arises primarily out of the size of the state space. So, there are various methods for to try to contain that state space, among which we studied a little bit the use of BDDs, right, and BDDs can represent the state transition relation in a canonical form, and then we can use that state transition relation to traverse the state space and find out the truth of different properties. Now, in spite of the representation that BDDs give us, typically for a large number of variables, if the number of state bits is large, then it is not feasible often to construct the BDD, because the total memory that the BDD requires becomes exorbitant. So, as a result of which there are attempts to partition the transition relation and store not just one BDD, but several BDDs for each of those partitions, and various other types of approaches are there to contain the state space while preserving that the state space is stored primarily in terms of the BDDs. But up to a certain point this works, beyond that we find that it does not work anymore. So, if you are able to construct the transition relation in memory, then your model checking works fine, because the BDD operations that you do thereafter using the state sets and then taking the AND with the transition relation, finding out the next state transitions or the previous state transitions, and then again extracting out the previous or next set of states, and then this is how we were doing the symbolic model checking, right. So, that works fine provided you are able to construct the transition relation in the memory as a BDD. If that does not work, in other words, if you are not able to construct the transition relation, then there are several alternative approaches, among which the most promising one that has been used in practice is called bounded model checking. So, the concept of bounded model checking in very simple terms is like this, that if I am not able to build the whole state machine, the transition relation of the whole state machine as a BDD, let us see what is the transition function specified by the user. See, every circuit description is a specification of the transition function, because it just tells you how the next states are going to be updated given the present state and the inputs, right. The size of this transition function is typically much smaller than the size of the BDD. Why? Because of state transition function is just a set of equations, and the size of that is the size of your code, say your RTL code. Okay, that is the size of the state transition function, but the BDD size grows much larger than that, as we know. So, therefore, if we could actually work on the state transition function to do this traversal, then our growth will be, with every time step it is just going to add a linear number of clauses, right, each time for the set of clauses corresponding to the transition function. Okay. That is the motivation of doing bounded model checking. Now, obviously, how many times are we going to do that? For one time step, for 2 clock cycles, for 3 clock cycles. So, that is the bound. So, we try to find out a counter example of length 2, of length 3, of length 4, like that. Iteratively, we increment the bound and try to find a witness of that size, right. So, at no point of time do we try to create the explicit state space, nor do we try to create a BDD of the transition functions, right. So, this is the philosophy behind bounded model checking. So, let us go through the details of bounded model checking. So, the broad methodology is like this: we construct a Boolean formula that is satisfiable if the underlying state transition system can realize a finite sequence of state transitions that satisfy the temporal property we are trying to validate. Right. So, we are trying to realize a finite sequence of state transitions that satisfy the temporal property. We use powerful SAT solvers to determine the satisfiability of the Boolean formula. So, I will explain what is the role of the SAT solver in this, but let us go through this first. The bound may be increased incrementally until we reach the diameter of the state transition graph. Now, what are the requirements for BMC? Specification should be given in temporal logic, system should be specified as a finite state machine, and we are given a bound k on the path length. This is a parameter of the algorithm. In bounded model checking, only paths of bounded length k or less are considered. What we do is we unfold the property into Boolean clauses over different time steps. I will show a procedure for doing that. We unfold the state machine into Boolean clauses over the same number of time steps, and we check whether the clauses are together satisfiable or unsatisfiable. Right. So, let us start with an example first, and then we will go into the formal procedure. So, this is our familiar example. This is a priority arbiter which arbitrates between two requests R1 and R2. So, it has two grants G1 and G2, and this is the implementation of that arbiter. The initial state of the arbiter is G1 is low and G2 is high. Okay. So, that is the initial state of these two flops, and we want to verify the following property, that when R1 is high, G1 must be asserted for the next two cycles. Right. So, in linear temporal logic, in LTL, we write that as always R1 implies next G1 and next G1. Okay. Now, first let us manually examine and determine whether this property will hold or not. Will it hold? Right. So, it will not hold, and the counter example is that if R1 is high in one cycle and low in the next cycle, then what happens is that in the next to next cycle G1 does not hold. Right. So, this property actually does not hold on this implementation. So, let us see how BMC will try to find this out. So, first thing that we do is we represent the circuit in terms of transition relations. So, this is exactly how in a typical RTL code the transition relation will be defined. So, it will be defined as a set of equalities like this, where the next state is assigned based on this. So, the next G2 is R2 and not R1, R2 and not R1 and not G1. Okay. And G1 in the next cycle gets the same value as R1. Right. The initial state is G1 equal to 0, G2 equal to 1. Now, what do we do? Just like we do in traditional model checking in the tableau method, we will first negate the property and look for a witness of the negated property. Right. So, if the property is this, then the negation of that property is future R1 and not next G1 or not next G1. Okay. So, this is the negation of the property. Now, what we will try to do is we will unfold this property over time steps, we will unfold the transition relation over time steps and see whether there is a satisfying witness in the conjunction of the two. Right. So, if we are able to find out a satisfying witness in the conjunction of the two, then we have found out a witness for the negated property, which means that the original property does not hold. Okay. However, if we are not able to find a witness of this, then what can we say? Can we say that it holds on this, that the original property holds on the state transition system? We can't, because we are doing it only for a fixed bound. So, maybe there is a counter example of longer length, right, but we can conclude this provided that we have explored up to the diameter of the state transition system. If we have explored up to the diameter and we have still not found it, then we can conclude, right. But then given a state transition system, how would we know what is the diameter of that state machine, right? It is not an easy task to determine that. So, the way that in which this is going to work is that we will assign a variable, the variables that we have, we will assign distinct variables for each clock cycle. So, for example, we have 4 variables here, R1, R2, G1, G2, right. 2 of them are inputs and 2 of them are state bits. So, G1, G2 are state bits, R1, R2 are inputs. So, we will say that R1 0 denotes the value of R1 in the initial state, R2 is the initial value of R2, G1 and G2 are the initial values of G1 and G2. Then at time 1, R1 1 is another variable, it is not the same as this variable is R1 0, R1 1 is another variable. And what does this variable represent? It represents the value of R1 in the next clock cycle, okay, in the clock cycle following the initial cycle. And similarly, R1 2 is the value of R1 in the second clock cycle. Similarly, R1 3, R1 4, R1 5, they are all distinct variables representing the value of R1 in clock cycles 1, 2, 3, 4 respectively. Is that clear? Similarly, we have for R2, for G1 and for G2, right. So, in each temporal world the signals have a different valuation. So, we assign a different set of variables to represent their values in that clock cycle, clear. So, what are we trying to find out here? We want to prove that for all t, R1 t implies G1 t plus 1 and G1 t plus 2, okay, that is the property that we want to prove, okay. Now, we start with the bound of length 2. So, let us say that our depth bound is 2. So, the question that we are essentially asking is there a witness of length equal to 2? So, we are going to create clauses from the transition relation, clauses from the initial state and clauses from the property. Clauses from the initial state is simple. We said that the initial state is G2 is high and G1 is low. So, the clause from the initial state is G2 0 and not of G2 not of G1 0. So, this is the initial state. What are the clauses from the transition relation? So, we are unfolding the transition relation only once here, because we are looking for witnesses of length 2. So, we are writing one clause as R2 0 and not R1 0 and not G1 0 implies G2 1. So, G2 is 1 in the next clock cycle, if in the present in the 0th clock cycle we have R2 is high and R1 and G1 are low. And similarly, we write R1 0 implies G1 1. Okay, so, these are the clauses C1 1 and C2 1 are the clauses from the transition relation. Now, let us see what is the clause from the property. So, if we have to have a witness of length 2 for this thing, which is the negation of the original property, then we need R1 in the first clock cycle and not G1 in the next clock cycle, right. This cannot be used because we are looking for witnesses of length 2 only, right. So, we write this as R1 0 and not of G1 1, okay. Is that clear? So, that is the clause that is generated from the property. Now, we pass all this to a SAT solver. Now, see, each of these clauses is a Boolean clause. There is no temporal operator involved in any of these, right. They are Boolean clauses over a set of Boolean variables. So, we can pass this set of clauses to a SAT solver and ask, is Z1, which is this one, let me take a pen. We ask Z1, which is this one, intersection I, this one, intersection C1 and C2, these clauses, whether this whole thing is satisfiable. And the answer is no, it is not satisfiable, because if you see that Z1 conflicts with C21. What does this one say? This one says R1 0 and not of G1 1, but this one says that if R1 0 holds, then G1 1 should be true, right. So, obviously these two cannot be satisfied together. So, there is Z1 conflicts with C21, so this is not satisfiable. So, what can we conclude from here? That it is not satisfiable? We can't conclude anything at all, because we know that there is no witness of length 2, but there can be witnesses of length 3, 4, 5, whatever, right. So, at this point of time all that we know is that there is no witness of length 2. So, then the option that we have right now is to increase the bound. So, let us increase the bound to 3 and then ask, is there a witness of length 3? Again we build clauses from the transition relation. So, C11 and C21 are borrowed from the previous iteration, we already have them. C12 says that if in cycle 1 R21 and not R11 and not G11, then in cycle 2 G2. So, it is the same this thing as before. So, just see, this was what we had previously, right. It is the same thing, except that this 0 becomes 1, this 0 becomes 1, this 0 becomes 1 and this 1 becomes 2. So, it is just a shift in the indexes of the variables, otherwise it is the same, because it is the same transition function, right. So, similarly we get C22. So, we add these 4 clauses as the clauses from the transition relation. Clauses from the initial state is the same as before, it is always going to be the same. Now, for clauses from the property, now this is what we have. We have R10, okay, and not G11 or not G12, okay. This is one way in which this can be satisfied, okay, and the other one is R11 and not G12. Actually, one of these subsumes the other, right, because you see this one actually will subsume this R10 and not G12 is there already here. Now, why did we have these two? Because this was the one that we borrowed from the previous one and this is the new one that we get. This is exactly counter example of length 1 and 1 or 2, this is for counter examples of length 1. Length 2 rather, this is for length 3, this is for length 2. Now, this one actually we have already tested and it is not there, right, but let us see for this one. So, okay, just let me revisit this thing. What we had here was that R10 and not of G11, okay. Now, what we have here is R11 and not G12. So, this actually is something which is triggering from this thing again. So, let me just write it out once so that it becomes clearer. So, see, the property that we had here was f R1 and not of x G1 or not of xx G1, right. Now, if I look at traces of length 3, all right, in what ways can this be satisfied? Okay. Now, one thing that you could have is R1 here and not G1 here, okay, and not G1 here, okay. This is one way in which you can satisfy this, or you can have R1 here and not G1 here, maybe G1 here and not G1 here. This is another way, okay. And this is F, remember, right. So, this can also be satisfied if you have R1 here and not G1 here, all right. So, one for the R1 happening here, the clauses that you get is R1 happens at time 0, okay. And then there are two possibilities. We have not of G1 1 or not of G1 2, okay. So, this is one possibility, okay. This covers these two, or the other possibility is that R1 happens here. So, that is R1 happens in time step 1 and not of G1 2, all right. So, if you see this thing here, then you will see that this is that first one for R1 0 and this is the second one for R1 1, clear. Then what we do is we again ask, where is Z2 and I and C11 and C12 and C21 and C22 satisfiable, and now the answer is yes, and the witness is that R1 0 is 1, R1 1 is 0 and G1 1 is 1 and G1 2 is 0, right, and the rest are do not cares. So, this is the counter example that we were expecting, right, that we were expecting that R1 is high in one cycle, low in the next cycle, then this assignment actually refutes the original property and therefore satisfies the negate, okay. So, the conclusion is that now we have found a bug. The moment we find a witness which is satisfying the counter example, so we have found a bug, okay. Now, what is the formal methodology? The formal methodology is that we have a bound on path length k, we have clauses describing the system M which has the initial state clauses which describes the initial state, they are Boolean clauses, and then we have the unrolled transition relation, the things that we derive out of the transition relation. These are the clauses derived out of the transition relation. And then there is an interesting thing, we need a loop clause. Now, why would we need a loop clause? If remember that we are talking about Bookey automatons, right. So, the acceptance criteria sometimes is not just a trace, but a trace with a loop, okay. Now, can you tell me one property where the witness is a trace with a loop? G of some P, okay. So, if I want a witness for GP, then I will need a trace with a loop, otherwise I can never say that I have found out a a witness for this. So, in other words, let us say that we are looking at a problem where the property that we want to prove is f of not p, okay. Then the negation of that property will be this, Now, to find out that whether there is a witness for this, this is what we are going to do. We are going to generate. So, what are we doing? We are generating clauses, right, and for each of these clauses we have the state variables S0 through some Sk. So, these are S00 to Sk0, then S01 through Sk1, and in this way we are going. Okay. Now, at every point, can we say that we have found a witness for GP? If you have found out a trace where P holds here, P holds here, and then P holds here, you still haven't found out a witness for GP. But if you can show that there is some state here which satisfies this, which is equal to some previous state, right, then then what have you done? You have actually found out a path, and then you have shown that there is a transition from this state to some previous state. If you have done that, then and if P holds on all of these states, then you have found out a witness for GP. And then you can say that I have found out at least one path where GP holds. So, in the Kripke structure, F naught P does not hold, because F naught P in a Kripke structure would mean that in each path in future I should have not P, but then I have found out a path in which in the future not P does not hold. So, it is always P. Is that clear? Now, let us understand that how do we do this loop detection. Now, see what is SAT trying to do? SAT is trying to find out valuations of these which satisfy the property constraints, right. And what is the property constraint here? We want to prove that for each of these states P holds, right. But then we know that just P holding on these states will not give me the witness. So, we must add clauses. Suppose this is the nth step. So, this is S0n through Skn. Then we must add clauses which says that S0n is equal to S00 if I want to check the loop for here, okay, and S1n equal to S10 and dot 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 Skn equal to Sk0. This whole thing, this is trying to see whether this state is equal to this, okay, or S1n sorry S0n equal to S01 and S1n equal to S11, and are you getting it? And then or, so this is trying to see whether this Sn is equal to S0, this is trying to see whether Sn is equal to S1, this is then the next clause will try to see whether Sn equal to S2 and so on, right. So, you are trying to see whether this last state is actually equal to any of the other states. Another way of looking at it is to check whether the transition relation rho, okay, Sk Sn to Si is true, and or over this for I equal to 0 to n. Now, let us try to understand what this means. What does this mean? This means if rho Sn S0 holds, that means that if this is my Sn, then there is a transition from here to S0. Okay. So, what I am trying to see is, instead of checking whether this is equal to this, I am checking whether there is a transition from this to this, right. So, transition from this to this, or transition from this to this, or transition from this to this, right. So, is there a transition from Sn to any of the previous states, and if we can get a satisfying assignment to that. So, what exactly are we trying to solve for? We are trying to solve for a valuation of these S0 through Sn such that for each of those valuations, P is implied by those valuations for each Si, and Sn has a transition to either of these, right. So, if we can find such a valuation of the variables, how many variables? N cross k variables, n time steps, k variables in each time step. So, if you can find out a valuation of these n cross k variables which satisfies both of these, then we have found out a counter example or a witness for Gp, and therefore, a counter example for F naught P. Okay. So, coming back to this, the loop clause, loop k is for all. So, here k is the bound, okay, k is the bound. So, for all I equal to 0 to k, there is a transition from the last state Sk to Si. So, for I varying from 0 to k. So, whether there is a transition from Sk to S0 or Sk to S1 or Sk to S2, or could be from Sk to Sk also, that self loop is also fine. So, is it clear? These are the clauses from the transition system and the initial state. This is the loop clause. Okay. Loop clause is not going to be added all the time. We will add it for specific properties like Gp. And Fik, let that denote that the temporal property F is true at the state Si, okay, under bound k or within the bound k. Okay. For the property F to hold on the system, M and Fik must be satisfiable. Remember that actually we are going to take the negation of that. So, now how do we translate LDL to SAT? So, this is the formal procedure for doing that. So, it is a set of rules. So, the first rule says, okay, if F is Boolean, what do? We just use the Boolean set of clauses and push it to the SAT solver, right. For the, if F is a Boolean formula, then we do not need to translate it into SAT, it is already in SAT, it is already in Boolean. So, we just pass it on to the SAT solver. If F is not Boolean, then we look at these things. Then what can it be? It can be XF or G of F or F of the formula or until, right. Now, if it is XF Ik, then we add the clause I less than k, because otherwise this has failed, right, and we say that F should hold in I plus 1, right. What does Fik indicate? Let us once again see. What does Fik indicate? It means the temporal property is true at state Si, right. What is this Si? This is the cycles S0, S1, S2, S3, okay. Each time frame is it basically at state Si means that at the ith time frame. So, Fik is true at the ith time frame if f is true at the I plus 1th time frame. Right. For this it is simple, f of Fik is true at the ith time frame provided that from in the time frames from I through k somewhere f of jk should hold, f should hold somewhere in that time frame. Okay. Otherwise within the bound k we have not been able to get a witness of this, right. So, given a bound k, this is how we generate the clauses, right. Is that clear? Gf of Ik is and over this thing. So, if Gf of Ik means that it should hold on every step, right, and then we add this clause loop k. So, this checks that f holds on all the steps from I through k, right, and then we also have a loop k. So, we are guaranteed that okay, from I through k in all the time steps, I will have this thing. In each of these this will hold, f will hold. So, f here, but that we know is not sufficient, because what we need also is that there should be a loop. Now, it could be looping to some state in between, because remember that the loop clause actually checks whether there is a transition from Sk to S0 or Sk to S1 or Sk to S2 and so on, right. Now, this loop k is always checked from k, the last state in your bound. Now, is that a correct thing to do? It is correct, because this state is always going to be in the loop. If you have a loop, then this one will definitely be in the loop. You cannot say about this one being in the loop. This may not be in the loop, but this one will definitely be in the loop, right. So, it is going to be something like this. This is how it's the infinite path is going to go, right. So, it is safe to say that I want to look at the loop clauses from with anchor at k. What about until? F until g I k is asking whether f until g holds in the ith time frame within a bound of k. So, then we say that for all j varying from I to k, gjk must hold. So, g must hold somewhere from I to k, okay, g must hold somewhere from I to k, and in all the preceding time frames f must hold. That is what this says, that there is some j where gjk holds, and for all the time frames n varying from 1 through j minus 1, f must hold in it, right. Okay. Now, that is all about this bounded model checking. So, you keep on now you see that with every each of these rules we are dropping one of the temporal operators, right. So, you have a finite number of temporal operators in your property. So, eventually you are going to be left with only booleans, right. When you are left with only booleans, you have generated the set of clauses. So, see, given k, you can use these rules to generate the set of clauses from the property for a bound k, right, and then unfold the transition relation up to bound k by repeating those things only by shifting the indices of the state transition function and take the initial state and then pass it all to the SAT solver and ask it to solve it, right. And when it returns that it has found a witness, then that witness translates to a counter example for your original property. Okay. Now, what are the advantages of bounded model checking? The advantage is that it is able to handle larger state spaces as compared to BDDs. Why? Now, we know that the BDD, when you take a transition relation and try to construct the BDD of it, the BDD starts growing with the number of variables, right, and that growth is typically exponential, right. Here also, with every time frame, the number of variables are growing. For one time step you had k variables, for 2 time step you have 2k variables, for n time steps you have nk variables, right. So, the number of variables are growing, but do we see a exponential growth? We see a linear growth in the number of clauses. So, where is the exponential gone? The exponential is for the SAT solver. The complexity of solving the SAT will grow with the number of variables and the number of clauses that you insert, right. The input size to the SAT solver is growing linearly, but the complexity of the SAT is growing exponentially, right. In BDD, the BDD construction itself absorbs that complexity. So, that is why the BDD size grows exponentially, right, and you see an exponential size BDD which you cannot fit in the memory. Here that space complexity is not there, because we are just adding linear number of clauses, right. And the SAT solver actually has to, where is the state space? Where is the state space gone? The state space is there for the SAT solver to explore the different valuations of all these variables for all these time frames, right. That is where, that is the state space that the SAT solver has to traverse, right. But then for SAT solving we have decades of research, more than 5 to 6 decades of research has been there on solving SAT, right. So, the SAT solvers are very efficient, in fact there are SAT solvers which are now tuned to BMC, because the kind of clauses that are generated out of bounded model checking, in the sense that you see there is similarity in the transition function clauses, there is a pattern, it is just a shifting of the indices, okay. Similarly, for a property there is a pattern in which the clauses are generated, right. So, given this pattern, there are SAT solvers which try to effectively use that information and solve the SAT in a better way, right. However, in spite of this, there are lot of problem instances in which SAT also cannot handle, because the number of clauses in a big circuit can grow very rapidly, and then even the best SAT solvers cannot handle it, right. So, I mean what we can say out of this is that, okay, the another advantage of BMC is that the witnesses produced are usually of minimum possible length, because you are iteratively increasing the bound. So, you will get a shorter witness, and which is easier to debug, because finally the verification engineer will have to see the counter example and debug that and find out where the error lies. The limitations are that it is sound but not complete, works for a bounded depth, okay, which is not bad actually, because many of the properties that appear in hardware designs have known time bounds. So, if this goes high, then you know that by what time the other signal should go down, right. So, that kind of information is typically available. So, that is why it is not, it is very useful in practice. So, for large depths the number of clauses can grow rapidly, thereby raising capacity issues. Nevertheless, SAT based FPV tools have been found to be having more capacity as compared to BDD based tools. Okay. So, with that we come to the end of the bounded model checking chapter. In the future we are going to look into some methods of abstractions and refinements by which we are able to handle large state spaces in a better way.